Alrighty, let's take up with example 3. F of x is equal to the square root of x. We want to find the derivative and state the domain of the derivative. Because they're both functions, they both have domains. Now, the domain of the derivative will be no larger than the domain of the original function. Can't possibly be larger than the domain of the original function. Oh, what is the domain of the original function? Well, you can't take the square root of anything less than 0. So the domain is 0 to infinity. I'm going to find the derivative by looking at the limit definition of the derivative. So the limit as h approaches 0, f of x plus h minus f of x, all divided by h. And that's from way back on slide number 2 here. F prime of h of x is equal to the limit as h approaches 0 of the difference quotient. So now we will calculate this limit. I have a difference of two radicals. How did we deal with those limits? We multiplied by the conjugate. Square root of x plus h plus the square root of x over square root of x plus h plus the square root of x. Don't forget to write down limit as h approaches 0 over and over and over again. So first, outer, inner, last, the middle falls out. We end up with x plus h minus x on top of the fraction bar. And I don't distribute because I know what's going to happen. I have x minus x goes away. Limit as h approaches 0, h over h and now I have an h on top, I have an h on the bottom, and I'm really happy because I get to cancel, and I really like to cancel. So now I have the limit as h approaches 0, 1 sitting on top. I have square root of x plus h plus square root of x. Now I have something that I can use direct substitution on. This is 1 over the square root of x plus 0 plus the square root of x, which is 1 over 2 times the square root of x. So, what is the domain of this new function, my derivative function? Well, I still can't take the square root of anything that's less than 0, but I also cannot plug 0 into that thing because it's in the denominator. So the domain is all positive stuff. So it's the same as the domain of the original function, but the endpoint gets left off. There are other notations that we use for derivatives. We can use f primed, y primed, dy dx, df dx, the derivative with respect to x of f of x. Honestly, I've never used either of these last two here, the big D or the big D sub x, but you might see it in a book somewhere. I will use all of these. So f primed or y primed, you just plop a primed on there. dy dx or df dx means you're taking the derivative of y or a function f with respect to x. If you see just a d on the top, that means you're going to be differentiating a function that's named next to it. So the f can be on top with the x, then it's representing the whole derivative there. They all represent differentiation. Even though it looks like a ratio, it's not. dy dx is just a little reminder to us that the derivative is equal to the limit as the change in the x's approach 0 of the change in y divided by the change in x. So the deltas transform into d's. If we want to find the derivative at a specific value, then we put this vertical line there and put x equals a. It's the same thing as f primed evaluated at a. It just allows us to plug an a in. You'd get a plain old number out if you plug it in. A function is defined to be differentiable if the derivative exists. So where are functions differentiable? Well, we looked at one earlier that had corners. It's not differentiable at corners because it's changing rapidly from positive to negative. And there's no way you can go smoothly from positive to negative at a corner like that because it's in a changing at a constant rate here, increasing, a constant rate decreasing, and at the corner, as you're approaching from one side, you're positive, you're always positive. As you're approaching from the other side, you're always negative. So if we look at something like the absolute value function, it looks like V for victory. And remember, another way to write the absolute value function is to write it as a piecewise function. F of x would be equal to x if x is greater than or equal to 0, and the negative of x if x is less than 0. So if we're looking at any value greater than 0 and we wanted to calculate the derivative, then it would just be the limit as h approaches 0 f of x plus h, which would just be this piece of the function. So x plus h minus f of x divided by h. X minus h goes away. H over h is just 1. Makes sense, because to the right of 0, the absolute value function looks like the identity line. So let's look at values less than 0. Then we're looking at this piece of my piecewise function. We would have negative x plus h, because we would plug x plus h into this piece, minus negative x, all of that living on top of h. So I have minus x minus negative x goes away. I'm left with minus h on top of h, which is minus 1. So we're differentiable everywhere bigger than 0 and everywhere less than 0. Now for the value of the derivative at 0, I'm going to go back to just plugging the a in like we did back in section 2.7. So this would be the limit as h approaches 0, and since the function looks different on different sides, I'll approach from the left and from the right separately. So if I'm approaching from the left, I'm using this piece. So it would be negative 0 minus h plus h, excuse me, 0 over h, which gives me negative h, negative 1. And if we're approaching from the right, it would be the limit as h approaches 0 from the right. We're using this piece. So 0 plus h minus 0 over h, which is 1. So you can logic your way through it. I wouldn't expect you to reproduce all of this to prove that it's not differentiable at the little point. It's not differentiable at the little point because the derivative is saying, ooh, I'm negative, I'm negative, I'm negative. Then it gets to that little point and it's like, oh, I got to switch to positive immediately. What do I do? So it's not differentiable.